So I'm technical manager. I'm a technical manager in charge of the radiochemistry laboratories that we've got in the school. We've got some laboratories up on the floor of this building, which is where we do the majority of our uranium and thorium chemistry. And as Lewis alluded to, we've got a fledgling facility across in another building, which is where we're going to do our work with higher actinides. So I like to term this higher actinides rather than plutonium. Let me just press my back. And that was. Hey?
Are you off?
No. And that facility is
the end of his talk.
Is almost operational, and it's been a long battle getting from a position of having in 2016 sort of some two-dimensional plans of what the thing should look like to 8 years later, three-dimensional room with some three-dimensional boxes in it, which 90% work and 90% are plugged in with sort of connections in the right place. What I'm going to do is I'm just going to quickly talk a little bit, the final bit of today's session, just on some characterisation. So I'm actually going to use a case study which is very related to what Lewis was talking about and what Paul was asking questions about, and it's irradiation damage in ceramic materials. So this is for actinide disposition. 2004 article in the BBC, Lewis has sort of talked about the need for proliferation, resistance, security of these things. There's some quite good examples of how this material can sometimes make its way out of the facilities that it's supposed to be stored into and into the wider society. So clearly the decision has been made now, I think the correct one, to actually dispose of this, get it out of the way. I can share these slides, but there's some interesting links on here to various bits and pieces. I think this is the report this is the quote that you were referring to from the Royal Society, which was the chances that the stocks of plutonium might at some stage be accessed for illicit weapons production is of extreme concern. They voiced that late 90s. It took another 10 years, I think, for people to kind of cotton on to the fact that we should be taking this seriously. Various policy changes, but it basically bottom line is we're down at the bottom now. Lewis, Rob Harrison, Sheffield, Manchester. We've got significant funding to actually move this forwards, which is great for all concerned. HIP, zirconolite is probably going to be the way forward for this. I won't dwell on that slide. What I've sort of spent a lot of my career looking at is what happens when you subject ceramic materials to irradiation damage. So I think one of the unknowns is what is the effect of radiation damage on properties. Okay, so this radiation damage is going to happen, but what is the knock-on effect going to be in terms of the properties of the waste form? So Lewis, and I guess a few people have talked a lot about this idea of durability. One of the key properties is if you lock it up in a waste form, whether that be glass, ceramics or cement, I guess, you want it to stay locked up, either encapsulated or immobilised in the structure. And if you can't do that, then you haven't got a very good waste form. But one of the key things is that making a waste form and then testing the properties at time point 0 might not be giving you very good representation of what's actually going to be happening at time point 10,000, 100,000 years. Okay. So what I'm trying to illustrate here is this is waste storage time, and this is displacements per atom. So displacement per atom, if you've got a DPA of 1, okay, it means that every single atom in the structure has been displaced off its original lattice position 1 time. Okay. So, and if we're talking about zirconolite here, which is I guess the preferred option for plutonium, it goes fully metamiced at about 1 DPA. Okay, so metamiced is natural terminology for amorphous, basically. So it's a glassy mineral. Okay, so if you look at waste storage time and you look at displacements per atom for zirconolite, I've got a blue bar here, and this sort of 10 to the 3, 10 to the 4 years is probably the time period over which your canister is going to fail. So whatever it is you've got around your waste form, whether it be a hip cam, whether it's stainless steel canister or whatever, it's going to start to fail. Water is going to get in. Okay. That time period is also consistent with the point at which your ceramic material is probably no longer going to be a crystalline ceramic. Okay. It's going to be amorphous metamint. Okay. So water potentially hits your ceramic material. It's not a ceramic anymore. It's actually an amorphous material. Okay, with some, I guess, some structure which is not crystalline anymore. Okay, so measuring the dissolution resistance of your ceramic. Well, I guess I'll pose the question: is measuring the dissolution resistance of your ceramic going to give you a good idea about what's going to happen at this period here?
You need to make a glass.
You need to make a glass. Okay, so you can't make zirconolite as a glass.
Probably not.
Probably not, no. Well, unless you cool it down very, very quickly or you make very small samples that you can multiply later. So the way that we've gone around this is to try to understand or try to be able to characterise our amorphized ceramic. We've used ion beam implantation. So I'll skip over this slide. There's lots of ways that you can simulate radiation damage, and obviously with a pollutant-loaded waste form, it's primarily alpha decay because plutonium is an alpha emitter. The thing we're using is charged particles, basically smashing heavy ions, heavy cations, bismuth, gold, krypton, into the surface of the material, and that simulates the alpha damage associated with the sibling nucleus recoil. So plutonium-239 decays by alpha emission to uranium-235, you get helium out. Okay, this is what's ploughing through your structure. Relatively short distances, but it's got high energy, and it will cause a lot of displacements. Okay, it's a sort of a percolation-driven transition. So each of these alpha decay events is going to create a small localized melted region. That will rapidly cool down, but over time you get lots of these little amorphous regions, and eventually you go from something which has got discrete bits of amorphization to something which is essentially all amorphous. Okay. This is what happens macroscopically. Pristine. This is zircon, courtesy of Boris Burakov in Russia. I think he's still at UoS-SHU.
Funny is that he left the Radium Institute, someone told me that, don't know where he is now.
Okay, he's somewhere in Russia still, I would imagine. But this is a zircon crystal, zirconium silicate. Time point 0, doped with plutonium. 14 months later, macroscopically, there's been some quite significant macroscopic damage to this. Cracking, expansion of the crystal, and it's a bit difficult to make out on these images, but bits have spalled off. Not a very good situation to be in. Now, zircon is a lot less radiation tolerant than some other ceramic materials, but this is an example of why radiation damage can be quite detrimental to properties. Okay. So we're simulating alpha decay here. So I guess the first thing a lot of people might say is, well, okay, how do you know that your simulation is actually mimicking your natural occurring alpha decay? So the way we simulate the alpha decay is using ion beam implantation. You start with an ion source. I'm not going to claim to understand how this works, but the ion source generates ions, and you can separate them out so that you can choose the ion that you basically smash into your substrate. So this substrate here is a little ceramic puck, probably 10 to 13 mil in diameter and several millimeters thick. Okay. So you generate your ions, you smash them into the surface, and you hopefully amorphize a surface layer. Okay. Natural zircon, time is increasing, time and dose are increasing as we move move down the board. Early time periods, you've got these discrete amorphous regions, okay, metamix. These regions over time increase in dose, get bigger, until the other end you've now got discrete crystalline regions. So you've gone from amorphous regions in a crystalline matrix to crystalline regions in an amorphous matrix. Okay? If you do this synthetically, reassuringly you get the same, you see the same kind of thing. So now this is with implantation, amorphous islands that grow, and then eventually you've just got some residual crystallinity in there. If you take it to completion, you can essentially make the entire material amorphous. Okay. So we've got some confidence that what we're doing synthetically is mimicking what would actually happen naturally, either from natural minerals which have got actinides in, or if you dope with actinides. Okay. So there's examples of samples where you see the same thing. You dope with plutonium 10 weight %, and you see the sort of same kinds of trends as a function of time. So I'm going to talk a little bit about lanthanum ferrate, because this is one of the materials that we've looked at. Perhaps not so representative in terms of a waste form, because that would never be a waste form candidate, but what we were interested as part of this is trying to understand what's the effect of the transition metal. So we've got quite a lot of evidence now to indicate that irrespective of the transition metal, you still see this type of amorphization and changes in structure. Okay. What I'm showing here is, are some people familiar with SHRIM, stopping ranging matter? Basically, it's a program that you can use to understand the ranges of the implanting ion as a function of depth into a material. Key takeaway thing here is this is the peak in the damage in terms of displacements per atom, okay, and this is the depth. So unfortunately, we can get an implanted region, but our implanted region isn't very big. So we have considerable hurdles to get over in terms of how we then analyse this. We can't use bulk techniques because we've got essentially a very thin surface layer, which is our amorphous layer that we're interested in, on top of a bulk pristine strand. Okay, you can tune the shape of this by altering the implantation ion, the energy of it, and the fluence. So by increasing the fluence, you can create a higher DPA. By tuning the energy in the ion, you can basically shift the shape of this as a function of depth into the sample and change the shapes. So the key thing to understand about, I guess, this material is I think the way to look at this is you've got iron octahedra, and you've got like a backbone of iron octahedra which essentially makes up the matrix, and then you've got these lanthanide cations that sit in these larger cavities. So what we're going to do is we're going to probe the iron. We're probing like the octahedral backbone of the structure. Okay. Some more proof here that we've actually got an amorphous surface layer, because obviously if we can't prove we've actually amorphized the surface, then we don't know what we're looking at. This is some transmission electron microscopy that was taken on a very thin lamella that was extracted out of the surface. Krypton ions are coming in from this direction. We've got bulk pristine ceramic here, and we've got a probably 500 or 600 nanometer thick surface layer. Electron diffraction tells us that the bulk is crystalline because we see spots in the electron diffraction pattern, and we see this diffuse scatter in the surface layer. So that gives us confidence that this is actually amorphous, at least by electron diffraction. Okay. So we've got some confidence we've done what we intend to do. You can also back that up with some XRD. Pristine, crystalline signature in the X-ray diffraction pattern, pristine, and then irradiated. This is a bulk measurement. So what we're seeing here is this diffuse scatter here is indicative of some amorphous character, and that's that thin amorphous surface layer that we're seeing. because we're doing this in a bulk measurement, we're also seeing the underlying substrate as well. But it's the appearance of this diffuse scatter under here, which is also backing up the transmission electron microscopy. So we've got some amorphous character, albeit a very thin surface layer. Okay. And the technique that we often use to probe, to provide a structural probe, is X-ray absorption spectroscopy. So, how many people in the room are familiar with this as a technique? A few people. Okay. It's an element-specific probe. Okay, so we can probe the local structure of a particular element in our material. Okay, so from the context of this material, we're interested in the iron, so we're going to look at the iron edge. And this is a typical X-ray absorption spectra. I think this is actually platinum, but the features are sort of ubiquitous. You've got an edge position. Okay, and the position of that absorption edge gives you some information about the oxidation state of the element. Okay, so if you've got a redox active element, 2, 3 plus in case of iron, the position of that edge will change in energy as a function of what the oxidation state is, or the average oxidation state. You then have the Zanes region, which is referred to as the near edge region. That can be used as like a fingerprinting tool. So you'll look at the Zane spectrum, and you can compare it with a load of known standards to kind of get some qualitative information about the local structure, and then you can fit the X-AFS region, which is where all the sort of the really quantitative structural information is. You can extract out those oscillations, and you can do some clever fitting to try to pull out some next nearest neighbours around your absorber, in this case the iron. So you can probe the next nearest neighbours, the oxygen octahedra, and then further shells moving out in space. Okay, so what I'm showing here is some standards on the top. So these are typical standards that are often used sort of widely in the literature. You've got combinations of oxidation state and coordination environment. So we've got 3 plus iron 6-fold, 3 plus iron 4-fold, 2 plus iron 6-fold, and 2 plus iron 4-fold. Okay, so those are kind of the 4 corners of our plot in a sense. Okay, what we're assuming here is we haven't got anything other than 2 and 3. So you can get iron 4 and 6, I guess. Paul, glassy, can you get that with glassy systems?
I've not seen it, but I'm sure you could.
I think there are some examples of ceramic systems where you can stabilise 4 and 6, but it's unlikely to happen in our system. So we've gone with our 2 and 3 oxidation state standards, and then here we've got our data from our ceramics. So we've got a data set for the pristine material and then the irradiated material. And a couple of obvious things to pull out from here. The pristine material, pretty much like the mineral standards, you've got quite a lot of sharp features, okay, which is characteristic of crystallinity, structural order on the long range. Whereas the irradiated sample, this looks very much more like a glass. So you've got quite broad, diffuse features, okay. Second thing to take away is that you've got a change in this pre-edge feature down here. And this pre-edge feature, which I've sort of magnified here, is really nice. There's a nice diagnostic tool. Okay, the shape of this, or the area under this feature, and the position of this feature in terms of energy, tells you something about oxidation state and coordination environment. Okay. So if we sort of extract out, or if we fit the pre-edge feature using fitting techniques, I guess we could probably discuss at length about the veracity of those fitting techniques. These are quite well documented ways of fitting. You fit a background, and then you fit some Gaussians or pseudo-void type functions underneath. I think, you know, the number of features that you fit to a first approximation doesn't necessarily matter. What we're trying to do here is capture the area under that pre-edge. Okay, and the average position of that pre-edge. Okay? So if we pull all of that information out, we've got centroid position, which is basically just the average position of that peak. We've got the total integrated intensity under it, and then we've got the four corners of our plot. We've got iron 2 plus in 6-fold, iron 2 plus in 4-fold, iron 3 plus in 6-fold, and iron 3 plus in 4-fold. Now you will notice that I've put these polyhedral shapes the wrong way around. That's an error on my part. Okay, so ignore the pictures. Look at the Roman numerals. Okay, so 6 to 4, 6 to 4. Okay, pristine material sits in the region of 6-fold coordination for 3 plus. As we irradiate, we're moving up this axis, and we're moving to something that is sitting more in a 4-fold or lower coordination environment. Okay, probably fairly sizable error bars on this for reasons that we've sort of kind of alluded to earlier. But generally, what we think we're seeing is not really a change in the oxidation state, but we are seeing a change in the local coordination environment. Okay. We can back that up with fitting of the X-axis region. Okay, so that was kind of sort of semi-quantitative in the sense that we're doing some peak fitting and we're extracting some numbers. What we can do is fit the X-axis region, and in simple terms, what's happened here is we've basically just extracted out all of the wiggles in this space, okay, and then converted them into oscillations, okay, which approximate to either a simple sine wave or a convolution of simple sine waves. Okay. Take-home messages: pristine. This is a complex convolution of a number of different sine waves, which is typical of a crystalline material where you've got short-range, medium, and long-range order. Okay. Irradiated sample. You can approximate this to just one simple sine wave, which indicates that basically you've got a much simplified structure, at least from the perspective of the order of the next nearest neighbours. Okay, so if we then do a Fourier transform of this, okay, we end up with something which approximates to a radial distribution function. So the way to read this then is that each of these sort of peaks, okay, is telling you the position of a set of next nearest neighbour atoms. Okay, so this is moving out away from the iron atoms that we're probing. This first feature here is your iron oxygen coordination environment. Okay, and then out to higher radial distance, we've got some other features in here, which is second and third shells. Okay. Obvious thing that we can see here is when we look at the irradiated sample, we've lost all of this information in here, which is basically simply telling us we've still got iron oxygen polyhedra, okay, but then as we move out to further distance, we've got a completely disordered structure. Okay, in the crystalline material, in here you've got iron-iron interactions and iron-lanthanum interactions, but those interactions now have been completely disordered. Okay, so you no longer see them. So what all of this is telling us is that there is significant structural changes when you go from pristine crystalline ceramic to irradiated amorphous ceramic. I guess it's not ceramic anymore because it's amorphous, but I guess there's a semantic argument in this. Okay. So significant structural changes when you amorphize material. So, coordination environment. We can also extract information about the coordination environment as well. Okay. So if we fit the area under this feature here, okay, or if we fit a structural model to it, we can extract out the area underneath that feature, and that translates to the number of next nearest neighbours. Okay. So if this is our iron oxygen scattering interaction, essentially the higher this peak, the more oxygens there are contributing to it. Okay, and nicely, there's also a shift in the position of this peak to a lower distance. Okay, so those two things are self-consistent. Okay, if you move all of the oxygens closer to the ion, that is consistent with having less oxygens around the ion. Okay. Octahedral coordination, 6 oxygens around it, takes up a larger volume than 4 oxygens in tetrahedral around the central ion. Okay. So that's the situation for iron. So what we're seeing basically is we're seeing amorphization of the structure. We're going from something that's crystalline to something that's pseudo-glassy, amorphous, metamix, whatever we want to term it. And we're seeing a structural change in the structural background going from octahedral coordination to something less than octahedral, probably tetrahedral. We see the same type of things if we look at other materials. So this is pyrochlore, okay, and here we're probing the titanium structural motif. And again, pristine material, titanium 6+, okay, octahedral titanium. As you irradiate, you increase the size of this pre-edge feature, which is consistent with a reduction in the local coordination number. And if you compare that with the titanium 5 coordinated standard, you can see that this is moving in the direction of going from 6 to 5. Okay. Again, you can plot that on a graph. You can plot lots of different standards of 6-fold, 5-fold, and 4-fold coordination. And as you go from pristine to irradiated, you're moving in this direction diagonally, which is going from 6-fold to 5-fold coordination. Okay, and that is unlike in iron, where the coordination number didn't change the energy position. In titanium, you do get, in addition to an increase in the integrated area, you also get a change in a shift in the centroid position as well. But basically, driving in this direction is going from titanium 6-fold to titanium 4-fold. Okay. We also didn't seem to see anything indicative of a change in the titanium oxidation state. So we think it's still 4, at least within the resolution of the measurement. Okay. Again, satisfy ourselves that we've actually amorphized the surface. We did some electron diffraction. Okay, so take-home message: we moved from 6-fold coordinated titanium to 5-fold coordinated titanium. Okay, and again, you can fit the x-axis region. The bond distance change that we're seeing again is consistent with a lowering of the coordination requirement. Okay, oxygens are moving closer towards the titanium. Is consistent with them being less oxygens around the titanium. Okay, so to sum all of this up, we've probed quite a lot of different materials. So we've looked at lots of different perovskites, manganetes, chromates, galates, manganate, iron. We've looked at lots of different transition metals in lanthanide perovskites. We've looked at titanium in pyrochlores, zirconolite, and everything that we've seen, if a material amorphizes, in order for a material to amorphize, you have to see a change in the coordination environment of whatever the backbone is, whether it's the titanium or the iron or the manganese octahedra, a change in octahedral coordination to something lower than, either 4 in the case of iron or 5 in the case of titanium. And I will bow down to probably Paul and Russell's greater knowledge of glassy networks, but to my limited understanding, if you want to support something that's topologically disordered, you can't do that with an octahedral network, because you can't create a disordered array with that. You have to have something which is either tetrahedral in the case of silicate glasses, they're all tetrahedral, or something which is less than 6. So situations where we've got 5. That's a very simplistic explanation. I think there's probably other things at play there. If we switch to something which is a zirconate or hafnate, so if we switch to gadolinium zirconate, which also has the pyrophore structure, but now you've got zirconium rather than titanium. That will not amorphise. Doesn't matter how much you hit it, damage it. You always retain something which is crystalline. Okay, and if you probe the zirconium local environment, it stays sixfold. And I'm not aware of any minerals where zirconium is in a coordination environment less than 5. So I think one of the key things here as to whether something will amorphise or not is whether the cations in the structure can support a lower coordination environment than 6. So something that is more akin to a glassy network. Some of this has been published, some hasn't. We've got quite a large body of work that we kind of need to work our way through. So that's all I wanted to say really. So I'm waiting to be shot down now by.
I don't think it's a case of shooting down. I think there is an interesting, as you put it, semantic argument about what is a ceramic in this sense, but also, of course, what you can't actually probe with this because you can't measure a TG. Yeah, I can't think of how technically you could measure a TG on such a thin amorphized regions. That's actually what you need to be able to measure to prove it's glass. What you're proving is you've got something amorphous.
Yeah.
And I think I agree about the topological arguments, but I'm not proving that something that is metamint is actually glass is a hard challenge.
Perhaps it's my sort of slack terminology.
It isn't. No, it isn't. When I'm teaching undergrads, I teach. A ceramic is a material consisting of at least one metallic and one non-metallic element formed by application of heat or heat plus pressure. Now, pressure isn't really the same as irradiation, and you haven't applied heat, although have you, because is there some kind of very localised heating?
You get localised melting.
Exactly. So again, we get into semantics. I think it probably is. But the fact is, if it looks like a glass and smells like a glass, it probably is glassy, isn't it? Or not.
So if we go back to what you were showing about the zirconolite, the iron seems to show like a disordered character, and the titanium is kind of left untouched. So I think that is telling you something about, I guess, what's the phrase I want to use? Iron will basically go into a lower coordination environment more readily than titanium. Admittedly, some of it is already in 5-fold coordination anyway in this combined structure because there's a 5-fold polyhedra. But I think there's quite a lot of stuff wrapped up in that. But I think it's all self-consistent, is what I'm saying. I think that.
And generally, in oxides, yes, for gases, you are then going to have low coordination numbers for a network formation. It is possible in halide systems to get higher coordination polyhedral flexible gases. So I think if you go to the sort of Z-band type systems, you start to get polyhedral that are up about 7 or 8.
They're crazy gases.
But
They are.
hopefully I've kind of finished the day bridging ceramics and glass in a kind of sort of slightly clumsy way.
And quite a lot of ceramics have glassy grain boundary phases anyway. That's
Let's thank Martin. So, thank you everyone for coming. I hope everyone's found it